So the mesenteries are really just the visceral peritoneum. And it's, so let me get into the, these are, when you're looking at all of these, they're all types of mesenteries, like the transverse mesocolon and all that. The true mesenteries are the ones that are holding the small intestines in place. So if you look at on page 908, really it does the best job of kind of showing you the side view. All of this that's in green here that's looping along, these are all mesenteries. Like the greater omentum is a type of mesentery. The true mesenteries are the ones that are holding the small intestines. So it's just visceral peritoneum, and it comes around like shrink wrap and it holds onto itself again. But the role is, you know, A, it's holding things in place so you can't have a loose tube that can tie itself in a knot, which would be disastrous. But it also is where all the supply lines are and what we stick our fat on. Okay? That work it? Okay. All right. What else we got?
I was interested to try and figure out where the, this is probably more of a lab question, but specifically the lesser and greater omentum in this case.
Oh, here you go. Look, it's right on this thing.
Yeah.
On the. So the greater omentum and the lesser omentum are both glued to the stomach. Okay. So the lesser omentum is glued to the lesser curvature of the stomach, and it just kind of holds it right up here. And then, because remember, if I've got this kind of double layered visceral peritoneum, it's coming down and it's wrapping around as it keeps going. Okay. So it's that greater omentum is really just where instead of coming straight from the greater curvature of the stomach to head over here to the transverse colon, it could have done a straight line, but instead it did this extra long loop and loop back on itself. So it kind of made a folded over apron. And that's just, it's a great place not only to have the supply lines of the veins, arteries, nerves, lymphatics, but it also is a fantastic place to put on fat. Because remember, our body's philosophy, you never know where that next meal will come from. Just biology, not reality now, at least for us. So far, never know. Could be the great starvation. Who knows? Probably not. All right. They'll keep making toilet paper and they'll keep growing things, I'm pretty sure, despite viruses.
Do the greater and lesser omentum also have like the blood supplies and things like that?
Yeah, yeah. That's what the supply lines. So veins, arteries, lymphatics, and the nerves, all of that. All the mesenteries have those, yeah. So mesentery is just kind of a huge umbrella, but the only ones that are called like the true mesenteries are the ones that are holding the small bowels. All right, what else we got?
What's the difference between A or B hepatitis?
Hepatitis.
Hepatitis.
Hepatitis. Don't get hung up on seeing the word. It's hepatitis. So hepatitis, those are viral hepatitis. There are lots of different ways to have hepatitis because hepatitis just means inflammation of the liver. Okay. But the viral kinds, there are a lot of them. It's kind of an alphabet soup now, but A and B are the ones that I've got on there. A is the fecal oral and B is the blood and body fluids one. So no matter what, they're still awful things to have, quite honestly. And they do set you up for downstream problems with liver failure and increase your risk of liver cancer. You don't want them. Yeah. But it is one of the things that has been treated with IgG, immunoglobulins. Makes you feel like crap, but it's better than being dead. So, okay.
Well, I did notice that the liver has two specific lobes to it. I am having trouble remembering which side does which functions. I know it's separated by the falciform ligament, but I'm not sure which specific lobe does which functions.
Well, they're all doing the same function. The liver is the liver. So the left lobe does have the caudate and quadrate, which add into it, but the liver is the liver. That's why you can be a living liver donor. That's not an easy sentence to say. A living liver donor. because you can just absolutely donate part of your liver and it will regrow, but not, it won't be the exact same shape. You get to do it once. But yeah, so the liver is the largest gland in your body, but it is, it's all doing the same thing. We're just divided up into the lobes. Kind of like the lungs have lobes and they all do the same thing.
Okay.
Okay.
Which one is usually donated?
It is the left one. That's a big deal thing to do. It's a huge surgery. It's also, it's a big deal to be a living kidney donor too, because the donor is kind of the forgotten patient, because for the recipient, they go in abdominally and they leave unless it's cancerous, they leave the other one in place and they just stick the other one in, just add it. But the one who's the donor, it's a retroperitoneal organ, so they have to carve through muscle in the back, and that's the person who really has the pain. They went from being perfectly healthy to being a post-surgical patient. So it's a big deal to be a living organ donor. It's a big deal. It's like, wow. I actually know a nurse who donated one of her kidneys to a friend. She happened to be a match, and oof, that's a big thing to do. So no endocrine issues? Everybody good with endocrine? No worries? Know your diseases? What the imbalances are? Remember, I wrote this test not too long ago because I had to put it into our system. And I know I asked about some diseases, so you better know them. Okay. And
Can we go over the diseases?
Might be smart.
Bye-bye. What?
Might be smart.
Huh. How about I say a disease, you tell me the problem. How about that?
Okay.
Okay, I'm going to do it randomly. Okay, so it'll be Sue's random thoughts, which is always an interestingly convoluted place to go. So let's see. How about Addison's? What's the problem with Addison's? Is it too much or too little is the first question, and then of what? Okay, too much, too little, and what gland are we talking about? Somebody.
Is it pituitary?
Nope, not the pituitary.
No.
Is that the one with the insulin in the hump or something?
Nope.
That's
Oh.
the adrenal.
Adrenal. Okay, so Addison's is an adrenal problem. Too much or too little, and of what?
I think too little of the glucocorticoids.
Yes, and?
Aldosterone.
Yes, and? The whole adrenal cortex is not working well, folks. Okay, Addison's disease is an adrenal cortex insufficiency, period. So what would you expect if you don't have enough going from the outside? What was the zone that makes aldosterone? What's the name of that one?
Zona fasciculata.
Nope, not for aldosterone. That's the middle one.
The one that starts with a G.
Yes, the one that starts with a G. Glomerulosa.
Glomerulosa.
Glomerulosa makes aldosterone. What is aldosterone's function?
Water retention and blood pressure.
Okay, water retention, because it's not directly water retention. Yes, it does lead to that, but why? What's it really doing? What does it directly do? That's the question you need to know.
Maintaining sodium.
Yes, you retain sodium, so you don't pee out the sodium. You tell the kidneys, hold on to sodium. And then water wants to follow it. Who let the water follow the sodium? It wasn't aldosterone.
ADH.
Yeah, ADH. So ADH lets the water follow the sodium. Okay, so aldosterone increases sodium retention. Okay, so from Addison's, if I don't have enough aldosterone, then what are my effects? What do I see? Just for the aldosterone piece. We haven't even gotten to the glucocorticoid piece yet. So now what?
Probably high blood pressure.
Okay, so what about the blood pressure? If I don't have enough aldosterone, which way does it go? I couldn't tell. Just about blood pressure, but what? Up or down? Not
If
enough
If we aren't
aldosterone.
retaining enough
If
water,
retaining
it's
sodium.
going up.
it's going up.
Going down.
Oh.
Down if you don't have water. Okay. Remember, okay. This is, remember, if I am holding on to sodium and water follows sodium because ADH lets it comes in, they're both talking to the kidneys, what happens to my blood volume? Does it go up or down?
Goes up.
Goes down.
Goes up,
Oh, right.
right? If I am not peeing out my sodium and I'm not peeing out my water, I'm holding on to it, it goes into my pipes. I have more fluid in my pipes. What happens to the pressure in my pipes?
Down.
Going down.
All right, let's go to a hose. Okay, so I've got a hose. It's going to be a soaker hose. My soaker hose has lots of tiny holes in it so that when I turn the tap on, it will allow for water to flow through the hose, and they're tiny little holes that let the water seep out and water my plants. Everybody with me on my garden? Okay, so now I decide that I want to add some more water. So I open the tap a little more. Okay, so now I've opened the tap more. The pressure is going more because I got more volume going through, right? Would you agree?
Mhm.
Okay, what happens to the water coming out of the holes in that pipe? Does it slow down or does it go farther out?
Go farther. Squirt.
Right, of course, it goes out farther, right? So now you start seeing little geysers of spray. Would you agree? Is that
Mhm.
the logic follow?
Yep.
All right. Why did it do that? When I added water, I added volume. What happened to the pressure in that hose?
Go up.
It went up. Okay. So let's go back to aldosterone. Aldosterone brings in sodium from the kidneys. Who follows sodium?
Water.
Here and all this other.
Water,
Water follows sodium. Who let the water in?
ADH.
ADH let the water in. So we've got water following sodium. It's in the blood, right? It's going to move into the blood. Now I've got more volume in my pipes. I ask again, what happens to the blood pressure?
Goes up.
Goes
Go
up.
up.
Yes, it goes up. Is everybody with me on this?
Yeah.
Yeah.
Okay, you got to be. This is huge. All right. Okay, so the pressure goes up. Okay, so if I have insufficient aldosterone because I have an adrenal cortical insufficiency called Addison's, what's my blood pressure like?
Down.
Down. What's my sodium level like?
Down.
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 What's my potassium level like?
Down.
Up.
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 Sodium and potassium.
Sodium,
go
potassium,
opposite.
like opposite.
Okay.
Yes, exactly. Okay, so I'm an electrolyte imbalance, a fluid insufficiency, a pressure insufficiency. That ain't good, right? Okay, so now the next thing that's missing in Addison's disease. So we've covered we don't have enough aldosterone. Now we don't have enough of the glucocorticoids. What do the glucocorticoids do? First, what do? Well, that was very teeny.
Stress
Try again.
levels.
Okay, so what about stress levels? That's too vague.
Cortisol.
Cortisol generally is
Yeah.
in relation with raising stress levels of the human body.
Okay, well, they have a correlation because as you get stressed, cortisol levels go up. That's why they call them the stress hormones. What do these cortisol, cortisone, corticosterone hormones do to you besides help you manage stress? That's too vague. What do they do? With a name like glucocorticoid.
Increase sugar
Yes, they increase sugar.
in the blood. Yes.
Okay, blood sugar. Blood sugar levels go up. Okay. When blood sugar levels go up, so it helps me with managing my, I've got a half a button here. That came off something. All right, anyway. So when we have an inability to raise our blood sugar levels with our glucocorticoids, because we don't have them because we have Addison's disease, how well do we manage stress?
Not well.
Not well. Okay, so you're not going to get the blood nutrient levels up as you were wishing. Okay, so now we've got insufficient blood pressure, insufficient sodium, too much potassium, insufficient blood glucose levels because we have Addison's disease. So we're not really your prime target for somebody who is going to manage a stressful position well. So it's kind of interesting that John F. Kennedy had it. Because I don't know about you, but I think being the president during the Cuban Missile Crisis was probably slightly stressful. So, you know, anyway. Okay, so Addison's disease. We've only done one disease, and so far, you're worrying me just a skitch, peeps. All right, so how about diabetes insipidus? What's the problem?
Decreased ADH.
Perfect. Decreased ADH. Okay, so what does ADH do?
Retain water.
Okay, retain water. Okay, so we've got ADH, we're retaining water. So now we have an insufficiency of ADH. So what do we look like? Give me those terms.
Edema.
Nope, not edema.
Polyuria.
Polyuria.
Oh, polydipsia.
Polydipsia. Anything else?
Polyphagia.
Nope, we're in diabetes insipidus. I made you walk right into that on purpose. Okay, so
Polyphagia.
there's no eating stuff. When you have an insufficiency of ADH, all you have is polyuria and polydipsia. So you keep peeing because you can't hold on to it because you don't have ADH. So then you're thirsty, so you keep drinking. Polyuria, polydipsia, polyuria, polydipsia, cycle, cycle, cycle. So these people have low blood pressure. They're constantly needing to pee. They have electrolyte and fluid imbalances, all right? They have very, very dilute urine, and it's constant. What's the other diabetes?
Mellitus.
Okay, so tell me about that one. What's my problem?
Decreased insulin.
Yes, decreased insulin. So now there are two different ways to have diabetes, right? There's insulin dependent and the non-insulin dependent. Let's do the insulin dependent because it's more straightforward. We'll start with that one. So what happened to the insulin dependent diabetic? Do they have beta cells?
No.
They destroyed.
No.
Yeah, these ones, if they are the juvenile onset type, the type 1, that they never had good beta cells once they started this disease because it's an autoimmune disease that put them into it. So they have no beta cells, so they can't make insulin. So therefore, they're insulin dependent. You can become insulin dependent and still have some beta cells, but we're going to go with the insulin dependent diabetic that is, we've lost beta cells. All right, so tell me, let me hear all the symptoms and tell me why we've got them. So first one is what?
Hyperglycemia.
Hyperglycemia, which leads to what?
Glycosuria.
Glycosuria, excellent. And you've got glycosuria because you've got hyperglycemia. So we've got osmotic diuresis, which means that we also have
Polyuria.
Polyuria, bingo. So then polyuria leads to polydipsia. Okay, and in that big sea of glucose, are the cells getting what they need?
Nope.
No, they are not. So if they're not getting what they need, then are they satisfied?
No.
No, so what do?
Gluconeogenesis.
Yes, they're starving, so they want gluconeogenesis, which just makes things worse, right? And what ketoacidosis can happen? Absolutely, because we're starting to break down what?
Proteins.
Fats. Glucagon leads to breakdown of fats. That's gluconeogenesis, okay, and ketoacidosis. But what else happens? What's that other P? We've done polydipsia, polyuria. What else?
Polyphagia.
Now it's time for polyphagia. Okay, you only get the polyphagia because your cells are still starving, even though they're swimming in a sea of glucose because they can't get it into them. Okay, we good?
Yeah.
All right, you've got to understand this stuff. I can't tell you how many diabetic patients we have. Diabetes mellitus is rampant. And a lot of them are non-insulin dependent, but they get into the hospital. And what will happen is you get somebody who has had some poor behavior choices for many years. They've been smokers, they're in heart failure, they have COPD, and they've been very sedentary, and they're now in in non-insulin dependent diabetes. So they're on the oral hypoglycemics. They still have beta cells. They still produce some insulin. They got crappy receptors on their cells, whatever. We treat them with pills. But then they get to the hospital. They can't breathe. We give them steroids. Glucocorticoids. What do glucocorticoids do to blood sugar levels?
Raise them.
Raise them. And if you're already a diabetic who's been handling things with pills, do you think that those pills are going to take care of their elevated blood sugar levels while we've added sugar to them? No.
Oh,
So they become insulin users while they're in their acute phase of their disease, and they panic because people think, oh my God, I'm on insulin now, I'll be on it forever. It's almost like you cross some threshold into another level of hell and you'll never go back. It's not true, but it is something that scares the bejesus out of them. And you will be dealing with these people in some way, shape, or form if you go into healthcare. Hopefully it won't be a family member or it won't be you, okay? But at least you'll get it.
both my parents are.
Yeah.
Both my parents are.
Oh, great. So you need to be careful.
Yeah.
Oh my goodness.
My mom is already on dialysis.
Oh, wow. How old's your mom?
She's like 75.
Oh, Daniel, how about your dad?
Oh, my dad is has a controlled diabetes. He's good. He's good.
Okay, but it's in your family. So I am going to hope that you are constantly monitoring yourself. Is that right?
Yes, I do.
Okay, good, because you are set up, son.
Mm-hmm.
Yeah, you chose the wrong parents for this one. Okay. All right, you've got to understand diabetes because we see it so much, okay? And the difference between why am I insulin dependent versus non-insulin dependent, okay? Beta cells versus no beta cells. It's a big difference. All right, let's see. How about, since we're in our world of hormonal problems, what is the cause of acromegaly? What's the problem?
Too much growth
Thyroid.
hormone.
Okay, too much growth hormone. What else? There's another piece to it that's vital.
Isn't it while you're an adult?
Bingo. It's while you're an adult. Because when you're a child, if you get too much growth hormone, what does that do to you?
Dwarfism.
Become a giant.
Dwarfism.
It makes you a giant. It gives you a pituitary gigantism. Okay. So acromegaly is the one that's really awful because you don't have the growth plates anymore. And so what you do is you thicken things. They get really large, hands, feet, and then their cranial vault starts getting thicker and it squeezes the brain, which will then herniate down through the foramen magnum. And that's pretty much we're toast. Okay. All right. What about Cushing's? Tell me about Cushing's. What do you know?
Increased glucocorticoids.
Yes, increased glucocorticoids. Okay, so increased glucocorticoids, what do they look like? Cushing's disease, what do they look like?
Moon face, they get the hump on their back.
Beautiful.
All I remember.
Well, that's not too bad. What do you think their blood sugar levels are like?
Probably very raised.
Pretty.
Very elevated, exactly. Okay. So then there are things that go with that too, just so you know, because we give this to people temporarily when we put them on the glucocorticoids, right? We give them a Cushing-oid syndrome, they call it, right? All those, back to those people that looks like they have diabetes, right? So with elevated blood sugar levels, the problem is that it sugarcoats your white blood cells, which then basically sticks them down and they don't work well. So if you have elevated blood sugar levels with Cushing's, what else are you open to?
Diabetes.
Infection.
Infections, absolutely infections. That's a big deal. Are you going to then maybe have some polyuria problems?
Yes.
Which means that you probably have some polydipsia problems?
Mm-hmm.
Yes.
And if you have a lot of sugar in your blood, it also draws water to it, right? Because water follows sodium and other solutes, which includes glucose. So what's your blood pressure like if you have Cushing's?
Increase.
No,
Decrease.
yeah. And then you've got so much pressure against some of the capillaries, then you get puffy, right? You get edema. Would that make sense?
Right.
And furthermore, with Cushing's, if you've got elevated blood glucose or cortisol levels and the blood glucose levels, it's supposed to normally be an increased rate of release in the morning to kind of give you your energy levels for the day, and then it tapers off at night. So how well do you think these people sleep? It's crappy sleep, right? Plus, of course, they have to keep getting up to pee. So they're awake, they feel good, except that they're sleepless. They can get cranky. They can actually kind of go into what we call a roid rage because they actually get sort of unbalanced because they're wired up and they don't sleep well. Okay, so let's see. How about myxedema? What's that? No, there's a kitty. Huh?
Doesn't that decrease levels of T3 and
Your
4?
T3 and T4.
Yes, exactly. You both got it. It's decreased thyroxine and triiodothyronine. So what does that do to you? Describe the person. What's the problem?
Sluggish and fat.
Okay, they're cold, sluggish, and fat. Yep, their skin, hair, they're really dry. So it's all because what do T3 and T4 do to you?
Slow metabolism.
They raise metabolism. And so if you have myxedema, you have slow metabolism. Okay. All right, let's see. How about what is Graves' disease?
That's increased thyroid and T3 and T4.
Okay, elevated T3, T4. So whatever we just said for myxedema, do we switch it for the Graves?
Yes.
Yeah.
Okay, and we get to add something else. So not only do we have we're hot, we're skinny, and we're going a mile a minute, but what other feature, what characteristic do you remember for that one?
Bulging
Yes,
eyes.
exophthalmia. Monkey eyes. All right. Okay, let's see. Going through my brain here. Moving on. We hit kind of the major ones. Can anybody think of anything that I've talked about that I forgot about? Let's see, if we go up here, there are a lot of things that can go wrong, but we just didn't talk about them. What do you think somebody would have? We didn't talk about this one, but let's see if you can just be creative. Think about this. What if you had a prolactinoma, which is a tumor that secretes prolactin?
Probably start lactating, frankly.
Yes, you would. Would it be a little weird?
Probably.
Yeah, you think? Okay. Okay. So I think we've kind of hit some of the major things with the hormones. So those are the screw ups. I was like screw ups. Of course, I'm going to pick talking about screw ups. So what else?
Summer has a question. She just doesn't have a mic.
Oh, okay.
So she was wondering if you could go over the second messenger systems about this CAMP and PIP mechanisms.
Sure. Okay. So let's see. Let's get to my picture. Okay. There's a lot to it, but I'm not going to go through every detail of it. Let's see. It's going to be probably close to here. Let's see. There we go. Whoop. Okay. Back up one. All right. Can everybody see this okay?
Mm-hmm.
Kind of gives you your where to look in your books, right? Okay. All right. The deal with second messenger systems, there's more than one kind, but the idea is the same. Okay. So what we've got is an amino acid based hormone that can't go inside the cell, because if you're an amino acid, you have a charge and you're too big just to waltz through the phospholipid bilayer. Okay, because remember the steroid-based ones, the cholesterol-based ones, they got to go inside and directly activate genes because they went through the plasma membrane, got escorted to the nucleus, and they did their thing. These guys have to ring the doorbell on the outside. Okay, so the cool thing about the second messenger system is, for instance, let's say I'm insulin. So I come and I bind to the receptor. And when I do that, it's like it's pushing a button and getting a whole mechanism starting to run. Okay. So it triggers this whole, there was a guy named Rube Goldberg who kind of did this weird thing with dominoes, or if you know the game Mousetrap, it's where you hit one thing and then this, goes to that, and it all starts until you go around an entire circle. And with Mousetrap, there's a cage that came down on the mouse. But second messenger system's kind of like that. And what it does is it allows you to have one binding of one hormone to the receptor, and it kicks off this whole amplification process. Because, you know, if you look at this particular one, which in your books is somewhere, let's see, over on page, let's see, where are we? I don't know. It's got to be somewhere in here. Oh, it's on page 605 in your books is where this picture is. But what happens is it amplifies the response, because all you got to do is activate this receptor, and it starts an activation process, which then leads to multiple activities. Because once I go through and I activate, in this case, the adenylate cyclase, then I start like a domino effect, where instead of having one domino knock over one domino and knock over the next to the next to the next, it's like this domino hits these two, which then hit these two, and it makes this huge spread out fan effect. So second messenger systems are a big deal because it's a characteristic of the amino acid based hormones, and it causes an amplification of the response inside. And it's called second messenger because it uses, instead of the hormone itself doing something itself, it uses word of mouth, kind of a chain of events. And this passing of the baton that they have up here is really a good analogy. So it says, okay, activates this, the G protein in this case, which activates the enzyme, which activates the second messenger, which goes out and makes things happen. Is that better? I added more words this time, I guess. Does that help, Summer? You'll have to text and send it across that way.
She said yes.
Okay.
For these systems, is the only reason why it's a second messenger system because the amino acids can't get into the cell?
Yeah, really. But it does give you that wonderful amplification from the outside effect. How about that? But yes, that's why it has to use a second messenger. It can't come in. You know, it's a lot like our coronavirus visiting with the people in the nursing homes now, honestly, because now you can't really talk to somebody directly. You instead have to, you know, send it through a phone or be outside a window, or, you know, you can talk to a nurse who can then convey the message to the patient. We're living kind of in a bit of a second messenger world in a way now. Make sense?
Definitely.
Yeah, these are tough times right now.
Are these reactions tend to be like shorter lived than the steroid ones?
Not really. Any hormone does its thing quickly, but the actual effects, you know, the duration, onset and duration vary incredibly, varying, you know, with what the hormone's job is, honestly. Because think about like epinephrine, norepinephrine. Their job is like you squeeze that out of your adrenal medulla, bam, right? You know, you get scared, you get boosh right now. Whereas, you know, you put out human growth hormone. I don't know about you, but I've heard of growth spurts, but I have never seen one where I just watch them and they go whoop, right? So, you know, it really depends, but it takes minute amounts of them. They don't actually hang around very long because they convey their message, and then if they are amino acid based and they do it from the outside, then they've done their thing. They go away, they get broken down, and the message is carried on inside, just sets the machinery in motion. If they're steroid based and they go in and directly activate genes, again, they set the machinery in motion. They just do it by turning on the genes directly instead of an indirect mechanism. Make sense?
Yes.
Okay. All right, what else? So are we great with endocrine? We know the difference between how we trigger stuff, the neural control, hormonal control, humoral control. Everybody okay with those?
I have a question about the paracrines.
Oh, okay.
Yeah, when you say local hormones, does that mean that the hormones that are being put out don't really travel long distances?
Exactly.
Okay.
That's exactly what it means. It's kind of like sometimes you'll have little nerve plexes right in an area. You'll have little communications right in an area. It's kind of like neighborhood versus statewide versus federal.
Is that kind of like hypothalamus to the adenohypophysis? Is that technically?
No, because yeah, that's a great question. But the paracrines tend to, instead of going into a vascular system, they do their effects really very locally. So they're kind of secreted into the fluids right around that area. They don't really flow into the blood vessels and get carried very far at all.
Okay, that makes more sense. Thank you.
You betcha. Those are things like my one that I keep beating on with the well, not just leukotrienes are one of them, but the prostaglandins. Those are paracrines. Both of those are paracrines. Or eicosanoids is another name for them.
Ладно, ты на видео.
So if you go through the different hormones, just make sure that what you know is, in essence, what's in that fill it in yourself table, right? So or if you honestly in your books, you know, the your tables that start over on page 612, they go through all the pituitary hormones. If you've got that table information for all these hormones, you've really kind of got it. As long as you got the diseases. And the disease, all you need to know is with the name, is it too much or too little of what hormone? And as long as you know what the hormone does, if you know the effect of a hormone, you know what triggers its release, what inhibits its release, and what happens if you have a surplus or an insufficiency. So all you really have to just basically memorize in the hormone team for job descriptions is who made it and what does it do. That's it. I know that sounds easy, but it's that straightforward. You know, when you're working, you have to know, if you're going to delegate, you have to know what their name is, what's their training level, and what can they do well, and you can trust them to do it. It's really all you're doing with the hormones. Who made it? So what's its name? Who made it? And what does it do? And the rest of it follows logically. And who's in charge of absolutely the whole shebang, really?
Hypothalamus.
Yes, ma'am. So, and remember, releasing hormone, inhibiting hormone, you're thinking hypothalamus. So the endocrine system is really fairly straightforward as long as you kind of put a table of who made it and what does it do, then the rest of it can be puzzled through. Of course, the more you have readily on tap, the faster you can get through questions, which gives you time to kind of ponder on the ones that are the stickier wickets, but nonetheless, okay? Good. Okay. I wanted to mention, I'll mention it again on Tuesday, but I'm going to go ahead and say, for one thing, we will be, as a college, we're going to be using this thing called Honor Lock. I don't know, have you heard about it much yet? I mentioned it a bit on Thursday. It's the proctoring thing, because I asked if everybody has a camera that will work, because if you don't, evidently the college will help you get one. I'm not sure, because it requires that, because what it does is it's basically watching you take a test. There's no real person, but I have not figured it out yet. Quite honestly, I've deferred that because I just didn't feel like it yet, but I will, because I've got to get that done. Because for the final exams in the last exams, so exam 4 in the final in lecture, and then for the last exam in the I think 3 and 4, we have to do that. And I have to comply with that stuff because it's basically what the college is doing. Okay, so it's going to require, so if you do not have one, I'm going to have to send out an email about if you have a need for a camera, it's going to happen. Okay, so if you guys are talking amongst yourselves and you know that somebody doesn't have it. Like I know Summer, you've got a problem with getting any kind of audio or visual, but I don't know if it's because of where you are and what you're doing now, or whether it's kind of like a permanent thing. So I'm assuming you can see me. It's just you're nothing but a black box with the word Summer in it for me. So anyway, it's coming. Okay, so since you came, I may as well give you that heads up. All right, so we've done, everybody's cool with endocrine. Any other questions, thoughts, concerns, whatever, with our endocrine world?
Well, Chelsea had a question, not about endocrine in the chat, but she was just wondering when we need a camera, a webcam, I guess.
Oh,
Soon.
well, first I have to make this whatever it is, the honor thing, honor lock work, but not for this exam 3 in lecture, but I'm thinking that by the time we get to test 3 in the lab, we may certainly by the last exams. Okay, so sooner is better. So and there are resources. I'll have to find out. I don't know if it says anything, but as I said, I have not played in this personally yet. I just know that it requires that you have a working webcam. So if your computer doesn't let you, that's where I think the college can help you get them. Not sure how. Okay, did that help?
If you go on, there should be a link somewhere on the college website, but there's like an emergency fund. I don't know if you can still do it, but if you want to look it up, you can like apply and say what you need help money-wise to get like school supplies, and they'll send you money. So
yeah, I think there's even a way to get the webcam sent to you, but I'm not positive. So I'm going to have to find out about that. Okay.
Well, I actually got an email from the college saying that they would provide the webcams.
There you go.
That was from Hannah.
But that wasn't like the My Courses email. That was like the SPC email.
Okay.
So like if you're in My SPC, if you click on the Outlook or the email web icon, that should pop up somewhere.
Okay, great. Thanks, Amanda. Yeah, everybody needs to, if I can't see you on this one, then I'm worried about you not having what you need, okay? You got to have that. Okay, so what else? So tables are huge. They're hugely helpful. I would definitely know my tables. Okay, and so then we jump over with digestive system. Everybody good with like the process of digesting foods? Do you know, like that homework that only some of you did? Everybody's still responsible for the information, whether you turned in an assignment or not. But you need to know what happens to each of the different food groups, how we break it down, and how we absorb it. And the how we absorb it is significant. Just saying, well, we absorb them in the small intestine, that's not enough, is it? Okay, because is there a difference? Do different things come in differently? Okay, be aware. I know I will ask.
Can we go over each of the different food groups from like how they're digested from the mouth to the anus? Can we do that?
We did actually.
Yeah.
So, and the table for that is on page 913.
That's good.
Okay. So yeah, we did, because I remember also at the very end of when we talked about digestion on Tuesday, it was, and I said, okay, big deal one is the weirdness of absorbing fats. And that was where I talked about the micelles coming into micelle. And that's how you bring in your fat soluble vitamins. And I remember chylomicrons with the protein coating, and that's how you chylomicrons and stuff. So that's and that's anything that's really special like that. Obviously, if I took the time, and I did it twice because I talked about it again with the metabolism thing. So I did it twice. And this would be the third time. You think I might ask? Thinking I probably am asking. Actually, I know for sure I'm asking because I wrote the test. So there you go. Okay, but you need to know who makes what hormones and what are hormones, digestive enzymes, and what they do. And is bile an enzyme? There's a basic one. No. I would really know about All Hail the Liver, by George. I would know the liver's functions. You know how I feel about the liver. I mean, I'm a great fan of the amazing things that the liver does. So therefore, if I were you, knowing my fandom base, I would really know about that liver, right? I mean, I know it's a scary place inside my head, but by now you probably should have some idea of what it's like to rattle around in there just a little bit. Embrace that. Okay. All right. What else? What about metabolism? Speaking of metabolism, anything? Let's see. Let's go to this. What's an essential amino acid? Why is it called essential?
Because you have to get it from other sources because you don't produce it yourself.
Bingo. You have to eat it. Yep. Okay. So what if you have someone who is battling the COVID-19 virus and they're in the hospital, are they in a positive or a negative nitrogen balance?
Probably negative.
Oh, yes, they are. Okay. What about the pregnant woman who is about to deliver, but she's still pregnant?
Positive.
She's positive.
Yeah.
And let's hope to God she doesn't get COVID. And she might be in balance, but not for a right reason. Okay, which of our nutrients gives us our biggest bang for our buck in the world of energy? And
Carbohydrates.
okay, lipids and why? Oh.
Because of the triglycerides that become acetyl-CoA.
And when you say acetyl-CoA, it's because of that first part of that word, right? The acetyl group.
So, yeah.
Yep, that's it. Because how many acetyl groups do you get out of a lipid? There's a technical term for it. Gobs. Kidding. You get lots. Because remember, think of those acetyl groups as those little 2-peg Lego blocks, right? Okay. So in each acetyl goes around. So if I have one glucose molecule, one C6H12O6, how many pyruvates do I get? 2. Okay. How many carbons does a pyruvic acid have? 3. How many ATPs do I have to invest to get this thing kickstarted? 2. How many ATPs do I net at the end of glycolysis? 2. There's a 2 theme, isn't there? How many NADHs do I create with reduction, with redox at the end of glycolysis? How many?
I feel like that one was the 8, but that might have also been 2, yeah.
Just 2. Yep, another 2. Okay, it was not a trick question, but it did fall in with the 2 category. All right. How many ATPs should we get from one NADH?
Is it like 2.5 or something?
No, well, just let's say 1. Yes, let's go with 3. Okay, you're right. You're not wrong in that, when we start averaging them all out, but let's just take the 1 and give him his full 3 credit, okay? When we decrease the numbers because some get lost because the ones from glycolysis were on the cytosol, right? Because Krebs cycle is in the mitochondria, but the glycolysis, they could get lost. So they kind of just averaged out we got lost, so we got nothings. All right, how many ATPs for one FADH2? 2. Back to the 2 theme. Who is the terminal electron acceptor after we're using ATP synthase? Yes, you got it. What is it?
Oxygen.
Oxygen. Okay. What's created when oxygen is the terminal electron acceptor?
Water.
Yes. What is the full chemical formula for the process of aerobic respiration? Oxidative.
Isn't it like glucose to water and CO2? Or is that glycolysis?
You're on the right track, but let's do C6H12O6 glucose plus what?
O2.
Okay, 6 O2s plus 6 O2s. Okay, and then through the magic of glycolysis, the Krebs cycle, the electron transport chain, all of that, we end up with
6H2O. No, 6 CO2.
CO2, 6H2O.
6H2O and 32 ATP.
Yeah, 32 to 38. You can end up with a whole bunch, right? ATPs. So lots. Okay. What if I caused histotoxic poisoning and you had cyanide, and so your electron transport chain didn't work? How many ATPs would you end up with? Other than the fact that you'd be dead. But let's say you're not dead. How many would you have without your oxygen?
2.
2.
2.
Why? Where'd the 2 come from?
The glycolysis.
Yes. Okay. Does substrate level phosphorylation have to occur in the mitochondria?
No.
Can it occur in the mitochondria? Does it occur in the mitochondria? Where?
Anywhere but the cristae?
Yeah, basically, I guess, but it's occurring as we're going through the Krebs cycle, isn't it? Right? So yes, your answer is absolutely 100% right. Plus, it's attached to, remember on that green circle, and it was down at the bottom where you had the GTP goes to GDP, so ADP can go to ATP. Substrate level phosphorylation, that borrowing from Peter to pay Paul now, so that then you worry about Peter getting his money back somewhere down the road. Okay. Which mineral do we find in the highest concentration in our bodies?
Calcium.
Huh?
Calcium.
Nope.
Calcium.
Calcium. And who goes with calcium?
Phosphorus.
Phosphorus. Calcium phosphate is bone. Okay. Hydroxyapatite. Okay. Why do you need calcium besides its role in being bone? What else do we use it for that you already know about?
Muscle contraction.
Perfect. Muscle contraction. What else? We're digging back to A and P1 now.
Absorb vitamin D.
Other vitamins absorb?
Okay, let's see. Well, you need vitamin D to absorb it, so it's not really what it does. Do you remember in the nervous system?
Yeah, I was gonna say that doesn't calcium do something with the brain? Like
It does. You need it in order to release neurotransmitters.
yeah.
Did we meet calcium in our first chapter this semester? I know we did. What did it do?
Calcium in the blood.
What role did it have?
The muscle contractions of the heart.
Yes, that too, but in the blood. You are right. It's important in any muscle contraction, whether it's smooth, cardiac, or skeletal.
I know you can get like calcium buildup, right?
Yes, you absolutely can, but that's a negative thing to have done. So
yeah, but doesn't calcium just like flow through the bloodstream?
It does. And why do we want calcium in the bloodstream? You're circling all around it. Can we clot without it?
No.
We can't is the answer. I kind of led you in that way, right? But you can't. Calcium is one of the factors involved in the coagulation cascade. So we use calcium for a lot of things, kind of my point. Okay. All right. Let's see. How about, why does sodium matter?
Follows water
contraction.
and all their
Okay, all those contractions once again, and nerve impulse because it's depolarization, right? And then what was our mantra?
Water.
Water.
Water equals acid.
Oh, well, that too. That's the other one. That's
Which
carbon dioxide plus water equals
water
acid.
equals acid.
This is the
water flow, sodium, and other
sodium,
solutes.
and other solutes. Okay, so sodium really pulls water. It's a really, really important osmotic factor. Okay. All right, let's see. All right. Tell me some amazing things about the resume of the liver.
What about the liver?
I want to know, give me its job descriptions, its resume. Let's go through its curriculum vitae, its CV. Let's start with, let's go with the metabolic stuff. It does make bile. Okay, so that's part of the, that's its digestive thing. What does it do with bile? What does bile do?
Emulsify fats.
Emulsifies fat, so it's detergent. Okay, so let's go into metabolic functions. What does the liver do for us?
Gluconeogenesis.
something with insulin.
Well, no, not so much.
Doesn't it make glucagon?
It doesn't make that stuff, but not, well, it does a little bit, but we're not going to talk about that. Instead, what we want to talk about is what's the effect of glucagon on the liver. What is the liver doing for us metabolically? Think about it.
Purify the blood.
Blood glucose?
It does purify the blood. What does that mean, though? You're correct. There's not, that's exactly right, but that's the really large job description. Let's get some detail credit for it.
Oh, doesn't it it like removes like bilirubin from blood?
Okay, that's not really the metabolic thing. That's more hematological, but okay, let's go with the, it takes bilirubin because it takes red blood cells, breaks them down, right? If the spleen didn't break them down, if we lose our spleen, the liver will take it over. Plus it takes the bilirubin from the spleen. Assuming
The protein activates, or the liver activates the protein breakdown, right?
Okay, gluconeogenesis. Yes, that's a metabolic function. Absolutely. So we store stuff in the liver. I was kind of looking for, metabolically, I'm looking for, it's a repository. It's where we store, what's the carb storage product called?
Glucogen.
Glycogen.
You're close. Glycogen.
Glycogen.
Okay? Glycogen is the starch of our animal bodies. Okay. What else does it store? So it stores starch, carbs. What else does it store?
Fat.
Fats. Okay, so we can break those things down. Plus, we can break down amino acids. Okay, what if you have just a whole bunch of that stuff? You've just eaten a great big meal. You've had a grilled cheese sandwich and some really greasy fries, and I don't know, whatever. So you now have all these carbs and protein and fat and all that stuff, and you broke it all down. Okay, so let's talk about what the liver does with it. So first off, when we absorbed through the intestinal wall, in the small intestines, we absorbed mostly in the duodenum and jejunum, correct?
Mm-hmm.
Right. Just as an aside, what do we absorb down at the end of that ileum? What's the big thing that the distal ileum is in charge of reabsorbing? Do you remember?
Bile salts.
Yes, the bile salts we recycle. Okay, so now we've absorbed most of our good stuff, but so let's go through the things that we're absorbing. So how does the amino acid get in? What's it go into? You got two choices. You've got the blood or lymphatics. What's it go into? Does it go into
Blood.
Goes into the blood. Okay, how about the triglycerides from the donut that you had for dessert?
That goes into the lymph.
Okay, how did it get in? Let's do the quick, what are the terms they called? So the fat comes in, micelle, and then it turns into a chylomicron, and then it travels through the lacteal, beautiful, which then takes it through, gets to the base of this thing. What's this thing called here?
The subclavian.
Eventually it's going to come up there, but what am I in? I'm drained from the intestines into the
Cysternochyly.
cysternochyly, and then I go to the
Thoracic duct.
thoracic duct into the
Left subclavian vein.
left subclavian vein. Awesome. Okay. Who came with the donut fat, those triglycerides? What other thing came in with it?
Sugar.
Nope.
Fat.
Fat is what we've already got in. So what came with the fat though? What came in through the micelles and then became part of the chylomicrons? What other kind of nutrient?
A protein. To make the chylomicron, is that what you're talking about?
Uh-huh. What else was inside the protein coating of the chylomicron? What else came in with the triglycerides in that micelle? What other nutrient hitched a ride?
Amino acids?
Nope.
Acids.
Carbohydrate.
Well, say it again.
I don't know.
Vitamin. Anybody want to say a vitamin of any kind?
Fat soluble vitamins.
Fat soluble vitamins. Name them.
A, B.
A, D, E, and K. Okay, cool. All right. So we got the fats in that way. How about the monosaccharides? Glucose, galactose, fructose. How'd they come in? We got to come through the intestinal wall. We go into what? If we're an amino acid, what did we come in? You got your two choices. Do we go into the lacteal? Do we go into the capillary? Blood capillary. Blood capillary. Okay. So all this stuff then comes in through the small intestines, right? So my chylomicrons with my fat and my fat soluble vitamins A, D, and K are going to take a longer trip, right? Because they're going to go up the thoracic duct. They're going to go into the left subclavian vein, which feeds into the heart, which is going to get down to the liver eventually. Okay. But the amino acids, the water, the minerals, the monosaccharides, those just drained straight in through that hepatic portal system, got into the liver that way. Okay. What does the liver do with these things?
It breaks
Quite a
them
journey.
down.
It stores them, right?
Mm-hmm.
So what does it do with the monosaccharides?
Turns them.
Stores
it
them
do?
in glycogen.
Okay, stores them as glycogen. What if I have plenty of glycogen? What will it make?
Does it make fat?
Bingo. Makes fat. Because remember, the big deal is that we've got these nutrient pools, right? So we can do all of this. Here I am just running my mouth instead of pulling through these things. Let's see. So here I'm just talking with Sue's random thoughts instead of actually providing something that might be useful. I've got pictures and I forgot to use them. All right, one moment, please. Let's see. So here's the absorptive states. That kind of is a good one to look at for just where everything goes. So I'm absorbing my glucoses. And remember, it's like nutrient pools. I can go all sorts of different ways, but the liver's at the center of it. So metabolically, it stores and it releases. If I've got enough amino acids of any particular flavor, let's say I've got plenty of leucine and isoleucine, will I store leucine and isoleucine as those things or not? Say no.
No.
No, I'm either going to turn them into energy or I'm going to, there goes the cat again. Okay, so I'm absorbing these things. They're going into the liver. The liver is going to do the magic with these nutrient pools, and I'm going to either store them as they are, or I'm going to move them into some other group, depending on what I need to do. Is everybody cool with that?
Mm-hmm.
All right. What does cholecystokinin do? I can't believe it took me this long to say that word. It's my favorite word. Cholecystokinin. Tell me about it.
Does it make the gallbladder contract bile?
It does. It makes the gallbladder contract. What else does it do? If I make the gallbladder contract, I'd better make something else relax. Would we agree? Otherwise, it's like squeezing a balloon and not opening the balloon. What's the balloon going to do?
So
Pop?
it's gonna end up opening that
The sphincter of Oddi.
Yes, the sphincter of Oddi. Perfect. Okay. So that's going to relax. It works with another hormone whose name I absolutely adore because it's such an obvious name to call it. What's the other hormone? Big hint. You can see my screen, right? What's this?
Secretin.
Yeah, CCK is cholecystokinin, secretin. Okay, so what does cholecystokinin do with secretin?
Stimulate protein and fat.
Okay, so it stimulates the pancreas, right? So we release the juices, the pancreatic juice with all those digestive enzymes. It also, cholecystokinin also stimulates the hepatocytes to do what? What do they do that's directly affecting my digestive process?
Is it to make more bile?
Yeah, exactly. Okay, because remember, I got to make the bile, I got to send it down to the gallbladder if I want to concentrate it, because it does a 10-fold concentration in there, right? Otherwise, you're doing that cheap store brand detergent. We want the good stuff, right? So cholecystokinin is a very busy hormone, okay? And I believe in your books, now I have to look here, but there's even a table that has all the roles. Yes, on page 888. It looks like, let's see, where is it? I think, do I have it? Let's see, I think it came to, there it is. Look, ta-da, 888. It gives you your job descriptions. It tells you who makes it. It tells you what it's stimulated by, which makes sense, right? Cholecystokinin, since it's really about getting my fats digested, it makes sense that when you've eaten something that has greasy stuff in it, right? Cheese. I would say that I am secreting cholecystokinin most of the day, pretty much every day of the week, because cheese is in almost everything that, every meal, because I'm a cheese addict, right? So you can see all the list of things it does. So if you look at cholecystokinin, which again, gotta love to say, it's going to slow down the stomach secreting a bunch of stuff, because its job really is to make sure that we are moving on safely. We don't want to have a bunch of hydrochloric acid. Instead, what we want is to deal with the fats. So we're going to deal with the gallbladder contracting, the sphincter of Oddi relaxing, right? Make more bile, release your pancreatic juice, all that good logical stuff that goes with, I just ate cheese fries, okay?
What happens to the bile salts that are absorbed from the ileum? Like, how do they go back to the liver?
Yes, because that's the enterohepatic circulation.
Okay.
Because remember, everything that is absorbed from the entire GI tract plus the spleen is going to get back to the liver through the hepatic portal vein.
And then are they just resecreted as bile, or do they need to go through some type of?
They'll be reformulated. They have to be reconstructed as bile.
Gotcha.
Because remember, we took the interesting coloring out of that so that we could make our feces brown instead of leaving it a sad clay colored thing. So it's just, we're recycling the building block.
Okay.
We have to refurbish it as bile. Okay. All right. Any other questions?
So the urinary chapter, that's going to be on the next exam, not this one.
Correct. Right. We will be starting it on Tuesday, but it will not be on the exam. Okay. The exam will open up at the very start of day on Thursday, and then it'll close at the very end of Saturday, because that's what we thought we would do for the exams. Quizzes can't follow that because we'll have finished covering the stuff. And so then I have to write it. And so it's Friday that I post quizzes. But the exams, this one will be Thursday through Saturday because we kind of agreed on that as a group. The final with exam 4 will be on the final day that we're supposed to have the final. Okay, so that'll be a one-time thing. Makes it easier for the whole, whatever that thing, honor lock thing is too, I'm sure. Okay. Okay. What else? What's gastrin do? I see gastrin up here. What's it do?
Stimulate the stomach to produce chloric acid.
Hydrochloric acid. Yes, it does that. Absolutely. So how does it know to do that?
By the pH of the stomach.
Bingo. So which way? pH too high, pH too low?
Too high.
Right.
Yep, too high. Other thing, because proteins especially will come in and they'll buffer the stomach. The other thing is, look at this little gastrin comes over here and it says relaxes the ileocecal valve. Now, why would the stomach want to have anything to do with the ileocecal valve, for God's sake? And what's this mass movement stuff? Why would it cause all this contraction of intestines, ileocecal valve relaxation, and mass movement stuff? Why would the stomach do that?
Well, because it still needs to maintain the flow.
Yep, it needs to move things forward. So gastrin, even though it's the stomach, you have a gastrocolic reflex. They are hooked together, and this hormone does that communication hookup. Cool, right? It's kind of nice if you're going to send stuff moving through the GI tract. It's kind of nice they don't hit up against a dead wall and they can't get through to the cecum.
So that's just to like make more room for when the stomach releases food into the duodenum, right? Or releases chyme into the duodenum?
Well, it's kind of, sort of. It's mostly, it's just about keeping the forward flow.
Okay.
In general, yeah. But stimulating the mass movements, remember with the duodenum, you've got that waves of peristalsis kind of flush things along. Well, you got the same thing in the colon too. They're called mass movements, where the haustral contractions, they lift something up and then it waves past, kind of like just being on a surf, right? And you kind of get left behind, but you've moved forward. So, and this whole release with gastrin and stimulating the mass movements, this is also, one of the reasons that some people cannot take a walk after eating, because there's such a strong stimulation hookup that it's like, yeah, I got to stay closer to a bathroom than this. Or else you have to walk with Depends, but that could get messy. All right. So that hormonal stuff that we talked about, I talked mostly about cholecystokinin, gastrin, and secretin, and then the histamine. Those were the things that I really hit on. So those are the things that if I were you, I would know about. We good? Name the water-soluble vitamins.
B complex and C.
Okay. What happens in the colon?
The absorption of water.
So that we allow for, what's the technical term for I suck the water out of liquid feces? What's that called?
Dehydrate.
No, that's a good general term. You're not wrong, but I want the one that's for the GI tract and what the colon does.
Reabsorption.
Yep, that's a real general term too. Not wrong, but not the one I'm looking for. Begins with a C.
Segmentation.
Segmentation begins with an S, although in English that C and that S do sound.
Compaction.
This is a hard C. It sounds like a K. Compaction, people, compaction. Oh my God, right? Okay, let's just do those terms, right? What's chewing called?
Mastication.
Mastication. What is swallowing called?
Deglutition.
Deglutition. Okay, what's the process of slow, sustained contractions of smooth?
Peristalsis.
Okay, what happens in the stomach? Why do I have that third layer of smooth muscle? The
segmentation.
No, not segmentation.
Churning.
Churning. Yeah, just take it like churning ice cream or butter. Okay, then we get to the small intestine. Now it's time for that S1. What was it?
Segmentation.
Okay, segmentation. Okay, so we do segmentation. Then we get into the colon and we do, begins with an A.
Compaction and
Compaction. And because we're doing that contracting of, what are those bloops called?
The hostra.
Hostral contraction with our mass movements, okay?
yeah.
We're doing compaction. Now, not only are we absorbing water, but we have the bacteria in there, our normal biome. And what do? They produce some stuff for us, actually, besides the methane.
They produce vitamin K.
Okay, and
I don't remember the other one.
actually some B vitamins. So they do some B, which are water soluble, and K. Why is it that you can take in as much vitamin C as you want, but you can't take in as much vitamin E as you want?
Those are fat soluble, so they stay inside.
Yeah, the fat soluble ones will store to toxic levels in the liver. So if you have not looked at the vitamins table and see what happens when you get too much or too little, you really ought to. It's kind of interesting. Because once again, I mean, if it's a screw up, that automatically makes it interesting. Okay, tells you what to watch out for. All right, let's see. So we've compacted. We've done the mass movements with the hostral churning, and we did the compaction. So what's our last step? Let's get out of here. What's the term for I left the anus?
Movements.
Defecation.
Defecation. Okay. All right. Do you know the entire alimentary canal, the tube, in order?
Yes.
Yeah.
Good. Then you'll get one of the questions right. Which anal sphincter do we have voluntary control over?
External.
External anal sphincter.
The external anal sphincter. What is the function of the pyloric sphincter?
Doesn't it?
Controls the flow from the stomach into the duodenum.
Yes, it controls forward flow from the stomach into the duodenum. Why do we need to do that? Why isn't it about backup?
Because
Very acidic.
It's very acidic. Okay, so you don't want to just dump, right? So one of the things the duodenum does is it sends the message to the stomach. You know what? You need to make sure that you've done plenty of processing and then slow it down when you deliver it to me, because a duodenal ulcer is a drag of a thing to have. Okay. Let's see. What's it called if you have an incompetent cardiac sphincter? What do you end up with?
heartburn.
Heartburn. What if you have chronic heartburn? What do you have?
GERD.
Yeah, what does GERD stand for?
Gastroesophageal reflux disease.
Bingo. All right. What are diverticuli?
Twisted of the intestine.
Okay, they're, which intestines do I find them in? Big or little? Small or large?
They're small.
No.
Large.
Large intestines. Okay, so
Large.
it's a feature
Yeah.
of the colon, a problem in the colon. And what is it that they look like?
I think they twisted and not enough blood supply go to the intestine.
Actually, what you're doing, you're describing a torsion. And a bowel torsion, that's a different thing. That is a holy crap, a medical emergency, because yeah, then you'll have your bowel will die. But diverticuli are not those. What is a diverticula?
Aren't they like little extra external, not really external, but pockets?
They are. They're like pockets.
Yeah.
You know, in a bicycle tire, especially an old style one. Let's pretend we're back in the 1800s, long time ago. Then you've got your tube, and if it had a weak spot, you would have it be like an extra bubble. That's a diverticulum. It's a weakness in the wall of the intestines, Okay, and remember, all the large intestine has is the circular layer, because the longitudinal layers become those two stripes called the tinea coli. Okay, and those little epiploic appendages, the fingers of fat, hang off of that. So you only have a single layer of the muscularis externa, and if that gets a weakness in it, and you get a bubble off of that, that's a diverticulum. And if you have diverticuli, you have diverticulosis. Why does that matter? What can happen?
If that ruptures, can that release bacteria into the peritoneal cavity?
Oh my God, yes. So what is it called if it gets inflamed? So I'm worried about the rupturing. So what?
Peritonitis?
Diverticulitis.
Diverticulitis. And then yes, if it ruptures, then I have peritonitis. Okay, so it's diverticulosis to diverticulitis to peritonitis. Okay, does that make sense? That's another common one. You know, and sometimes people have such bad diverticuli, and you know, even though they're careful with their diets and they avoid, you know, like eating nuts or any, you know, thing with seeds that would be small and lodge in there, they still just have really problems, and they'll cluster sometimes. They'll have to actually take out that chunk and re-anastomose, pull the two ends together without that bad spot in order to fix the problem. Okay, because it really is a dangerous, and it's very, very painful. From everything I've heard, it's just really painful. Okay. So that's a good screw up to know about. Let's see. What is the hormone that's in charge of the post-absorptive state?
Glucagon.
Glucagon, very good. What helps it? You're right. Glucagon is the number one thing to think about. Now, who else will raise blood nutrient levels?
Cortisol?
Absolutely. Glucocorticoids, because you're stressed. What else? Isn't it wonderful how all of this is so interrelated? The hormones are all the way over in the digestive system. I can't believe it. Okay, so we talked about being hangry. You remember this conversation from here? So who else would be involved? What other chemical mediator would be involved in raising your blood nutrient levels? You ever seen somebody who's angry? What do they look like?
Red.
Okay, what else?
Puffing and
Huffing and puffing. So in my nervous system, what do you think they're working with?
Epinephrine?
Yes, this is sympathetic nervous system. Epinephrine, norepinephrine, right? Up go your blood nutrient levels. So that's part of the post-absorptive state. Growth hormone also raises blood nutrient levels and then helps you build them. All right. Who's in charge of the absorptive state?
Insulin.
Yes. And how long is the absorptive state from when you eat?
Like 4 hours.
Yeah, about 4 hours. Think about your meal times. When do you start feeling hungry? And I'm not talking about I'm bored, so I need to eat, and trapped in my house, so let's see what's in the pantry. Or I can't look at this one more minute. I'm going to go find something to eat, kind of studying habits. By the way, I don't know if I ever had this talk with you guys, but you know, when you're trying to study this stuff, you can't be sitting for hours at a time. You just can't. Your brain shuts down. You know that, right? Okay. So a few minutes at a time. And if it means that you study for 10 minutes and then you get up and make a cup of tea and then sit back down, that's perfect. Okay. If it means that you're studying, you go get a beer, that's not so perfect. But anyway, okay.
guilty.
How do we lose most of our heat?
Radiation.
Most of it just drifts away, doesn't it? Okay. What is it called when you sat your butt down on where somebody else sat and it feels nice and pushy warm?
Conduction.
Conduction. In the world of lipoproteins, which ones do you like better and why? You got
those are the high HDLs and the LDLs.
You like the HDLs.
You want the HDLs. You want your high density lipoproteins high. You want your lows low. What are VLDLs?
Very low.
Very low. Are they okay? Say yes initially. Why do I mean yes initially?
Don't they turn into LDLs after?
Yes, exactly.
They do.
They drop their stuff off in the adipose tissue, which is marvelous. Off go the triglycerides, but then they turn into LDLs, and then we're back in, we don't like those. All right, I'm just sort of flipping through a page here and there. On page 956 is a really nice table of the major metabolic functions of the liver. What a great table. I love that. Let's see, what else do I like in here? Do we need fats in our diet at all? Can we just avoid them? Because they're bad news, right?
No.
No, you need fats.
We do, because linoleic and we have some essential fatty acids. Let's see. What else? Something else flitted through my brain. Let's see if something triggers it in here. Oh, why do we need cholesterol?
The
It
brain.
produces, right?
It does what?
Produces hormones, the steroid hormones.
Absolutely, the steroid hormones. Okay, what else?
Bile salts.
Absolutely, what else?
They're in the cell membranes.
Ooh, they do. They stabilize the cell membrane. So we do want, cholesterol gets a bad rap, and we make most of it. Once again, all hail the liver, right? It's in the liver's job description. Woohoo. All right, let's see. What about, which one would you rather have, heat exhaustion or heat stroke?
Heat exhaustion.
Yes, indeed. Why? What's heat exhaustion and what's heat stroke?
Well, I know heat stroke's bad for my residents.
Bad for everybody.
Heat stroke is when your body can't get rid of the heat, so it stays inside, correct?
Correct. And it's when the hypothalamus loses control. You go into a spiral. They are hot and dry. What's heat exhaustion? Why is that a better one to have?
Well, because you're like sweating it out, but you're dehydrated.
You're dehydrated. You're still in control. You're just dehydrated. Get inside, get something cool to drink, replace your fluids, and you'll be okay. But heat stroke can absolutely kill you. If I take your temperature, which is the most accurate way to get it?
Rectum.
Okay. Has nothing to do with anything on a test question, but what color thermometer do you want people to use? Which probe?
Red.
Yes. Okay. All right. Let's